page 23 of the scheduling notes, the last page. So let's talk about the implementation of a preemptive EDF scheduler. So you are scheduling by the deadline, so you need to know of the active tasks or the tasks that have been released, who has the closest deadline. So it makes sense to keep them sorted by deadline. And to do that, you can use a priority queue. You think that you learned about min heaps in your data structures course. And then you also need to keep track of when tasks that are not running next need to be released. And so you'd use the timer for that, and there would also be, again, a queue that's sorted by their next release date, and then the timer would be set for whichever release date was closest. So 2 priority queues. So one would be the ready queue, and this would be the ready task sorted by deadline from closest to furthest, or smallest to largest. And 2 would be the waiting queue, and this would be waiting tasks, or tasks that have finished their execution and are waiting for their next release, sorted by release date, when we got smallest first. So the scheduler overhead at each invocation of the scheduler is going to be, I said you can use a min heap, so that would be log n. So this is assuming that a min heap is used. And actually for my PhD, one of the things that I did was I implemented an EDF scheduler in hardware. This was on an FPGA. So most of the kernel was in software except for the scheduler part. And so I developed this systolic array implementation for a priority queue, and it was actually probably the high point of my research career. So published it at FPL and the Netherlands, and then that was that. So the advantages of preemptive EDF are that you have explicit deadlines, which is how real-time applications really should be thought about and described. So events happen and you need to react by a deadline. Also, it is an optimal scheduling algorithm. No other scheduling algorithm can do better. There is an equivalent scheduling algorithm called least laxity first. So the laxity, or the slack, is the amount of time from now until the task deadline minus the task execution time. So that's, or remaining execution time, so how much slack it has. So whichever task has the least slack, you could schedule that to run, and that's also optimal. And a third point is that it has the fewest scheduler invocations. So with fixed priority preemptive, your scheduler basically runs every time slice, maybe more often if tasks are blocking halfway through a time slice. And even if your scheduler decides to, well, your scheduler might decide to just run the same task again at the end of the time slice because there's nothing else of equal priority that's ready. But in any case, EDF has the fewest context switches. and it's got one main limitation, and that is the complex schedulability test, if you're not going to assume that deadlines equal to period, which in most real-time systems you don't want to have to make that assumption. So that's the end of scheduling and the first half of the course.